Greetings, ladies and gentlemen. In this video, we will be going over one of the two comparison tests, the direct comparison. Now I say one of the two because the other type of comparison test is the limit comparison test, okay? Now, direct comparison isn't too bad. What happens with the direct comparison test, it says that our series A sub n has to be positive and it has to be less than B sub n, less than or equal to B sub n. Well, what is B sub n? Where did this come from? The idea is that this is called a comparison test. So we take a series that is given to us and we compare it to a series that we know the behavior of, okay? So a series that we can easily tell if it diverges or converges, okay? And let's look at an example. If we are given sigma n equals 3 to infinity 3 over the square root of n squared minus 4. Now this is our a sub n. We have to find a b sub n to compare it with, okay? But before we do that, these are the two conditions that they give you. That if b sub n converges, then a sub n has to converge. If a sub n diverges, then b sub n also diverges. Now, that can sound a little bit complicated. Okay, what I just did was I broke it down into basically something that sounds a little bit nicer, something that sounds a little bit easier. So I said that if our given series, so when I say that, now the first one says this rule basically sums down into if we are smaller than a convergent series, then we converge. Okay, so smaller than a convergent converges. Okay, and that's talking about a sub n. So if a sub n is smaller than a convergent, then we converge. B sub n would be the convergent one. So if we are larger than a divergent, then we diverge. Okay, now say this to yourself a couple of times to just get this in your head. Smaller than a convergent converges, larger than a divergent diverges. Smaller than a convergent converges, larger than a divergent diverges. All right. And again, this and this is talking about the B sub n series. Okay, because B sub n we already know the behavior of. Okay, but how do we find out what is a good series to compare this to? Well, the idea is that you want to take the terms that have the most influence on how the numerator and denominator shape the series out to. It's essentially what has the most power to shape the series, okay? In the numerator and the denominator. So the idea is in this denominator. So let's say we want to put this compare to. Okay, what are we going to compare this to? I will compare this to, there's nothing that we could do with the top, so let's just keep it the same. 4 is simply a constant. What is more powerful? What is more influential? An n squared or a 4? Well, definitely an n squared because that's a variable term that's raised to the second power. 4 is simply a constant, so we can kick the 4 out. So 3 over the square root of n squared. Maybe we can compare to this. Well, let's look at this. This simplifies down into 3 over, what's the square root of n squared? Well, the square root and square cancel each other out, leaving us 3 over n. Well, hold on. This looks like a series that we know. This looks like a harmonic series. Harmonic series always diverges. All right. If you have a question about what the harmonic series is, you can view our video on harmonic series. So this series is divergent. Okay, so diverges. Okay, now one thing I would like to say is, if either of these two conditions are not met, then our test fails, or in other words, it is inconclusive. Okay, so B sub n diverges, so this is a divergent. Okay, so I'm going to write divergent. Now, how do we know if something is smaller or something is larger? Well, we compare them. Okay, we have 3 over the square root of n squared minus 4, our first one, and I'm just going to draw an arrow. This is our a sub n, and then these two, either one of these is our b sub n. Okay, compare this to 3 over the square root of n squared. Now I'm just going to say the square root of n squared, just because it looks a little bit nicer. It looks a little bit more uniform when comparing these two. I could have said 3 over n, same thing. Okay, it's just my decision here. Now, when we're comparing these, let's look at these. These two terms are fraction. These two series are in fraction forms. And we have to look at which one is essentially the largest one without plugging in numbers, without substituting numbers. We can if we want to, but without doing it in this case, let's look at this. N squared minus 4. Okay, that means that this denominator is smaller than this one. If we have a smaller denominator, that makes a larger fraction. Okay, now think about this: 1/2 and a 1/6, or excuse me, let's make it a little bit nicer. See how about a third? Well, a half in decimal is 0.5, a third in decimal is 0.33. Continuing. Now, the smaller the denominator, the larger the fraction, the larger the number. The larger the denominator, the smaller the fraction. Okay? So in this case, we have a smaller denominator because 4 gets taken away from n squared. So because we have a smaller denominator, this fraction overall is larger. Now let's look at what we're saying. We're saying that this series is divergent and this one is larger than the divergent. Okay. So in other words, if we are anytime larger than a divergent, okay, so larger than a divergent, we diverge. Larger than a divergent, we diverge. Okay. Now let's say that we were having some trouble figuring out the signs just by looking at these in terms of fractions. Let's maybe substitute a number in there. How about let's do, on this interval, let's substitute a 3. So this becomes 3 over square root of, well, 3 squared is 9, so 9 minus 4 is 5. Okay. And then we have 3 over the square root of, okay, well the square root and square cancel out, so that's just a 3. So this is 3 over square root of 5. 3 over 3 is simply 1. Okay? Square root of 5 produces a irrational decimal. When we divide these, okay, I'll let you prove that yourself. And when you divide this, 3 over the square root of 5 comes out to be larger than 1. Okay? And I'll let you, like I said, I'll let you prove this on your calculator. So that was our first example. Okay? A couple more examples remaining, just actually 2 more. Next one is kind of similar. If we have sigma 10, n equals, let's start from 2, over the cube root of n minus 1. Okay, this goes to infinity. Now, what is this? What is this series similar to? What can we compare this with? Well, 1 is simply a constant, so we can get rid of the constant. So let's say we can compare to, let's compare this to 10. Let's keep the numerator the same, because there's only one term in the numerator. So, but how about let's compare this to 10 over the cube root of n. Okay, do we know how that behaves? Let's rewrite this a little bit. Let's say 10 over n to the 1/3. Whoa, this looks like a p-series. And p, in this case, is our 1/3. And for the p-series test, we know that if p is less than 1 but greater than 0, so between 0 and 1, then our series is divergent. So this is a divergent series. Okay, this is a divergent series. And I just proved that by the p-series test. Now, let's compare these two. So if we have 10 over the cube root of n minus 1 compared with 10 over the cube root of n, right? Again, this one is a smaller numerator, therefore it is a larger fraction. And again, like the last case, we have a series that is larger than a divergent series, because we've determined this already diverges. If we are larger than a divergent, then this diverges, then a sub n diverges. Okay, so our answer for this series is that this a sub n diverges. That's our answer. Okay, because if we are larger than a divergent, we diverge. And if you want to, because I didn't substitute any numbers in, just looked at this analytically, if you wanted to substitute numbers in, you're more than welcome to do that. Now, our last example is our last example is a little bit trickier. Okay, so if we have sigma n equals 0 to infinity of e to the negative n squared. Well, this is an interesting one. Doesn't look like we've ever seen anything like this. But let's try to simplify this. This looks something like sigma n equals 0 to infinity 1 over e to the n squared. Okay, so now we're getting somewhere. Let's try to compare this to, so we're going to write compare to, let's say, sigma 1 over e to the n, right? We can use that to compare it to. And then what we can do, let's rewrite this. 1 over e to the n can be rewritten as 1 over e all to the n power. Why? Because when the n, by rules of fractions, or excuse me, by rules of exponents, when the n comes down, we can simply get 1 to the n, or 1 to any power is always 1. So we can rewrite it like this. All of a sudden, this looks like a geometric series. Why? Because we have r to the n power. So if we have sigma ar to the n power, we have a geometric series. This is perfect. Why? Because for geometric series, how do I know if it converges? Well, the absolute value of our r term has to be less than 1. So is the absolute value of 1 over e less than 1? Yes, it is, because e is roughly 2 point something. So this is less than 1. 1 over 2, let's say, gives us something around a half. So it is less than 1. So this is, because r, actually I should erase that. Because r is less than 1, this is a convergent series. All right. Now let's compare this series to this one. So we have 1 over e to the n squared. Let's compare this to 1 over e to the n. And this is a little bit trickier example. 1 over e to the n squared. Okay, which one has the larger numerator? Well, obviously this one, right? Because this one, or excuse me, which one has the largest denominator? This one has a larger denominator, seeing as how it's n to the second power is just n over here. So therefore, we can say that because we have a larger denominator over here, it's overall a smaller fraction. Okay? So in other words, a sub n is smaller than a convergent series. So if we are smaller than a convergent, our series converges. So a sub n is smaller than a convergent, right? Because this is convergent. So smaller than a convergent, we converge. Therefore, a sub n converges. All right. Now, like I said, this was a little bit trickier example. There was a little bit of rewriting to do. This was kind of a jump. But the idea is that the previous two examples had the p series. I figured why not introduce a geometric series here. Okay. Now that will be all for the direct comparison test. If you have any questions, please let us know. We'll be more than happy to answer them.